Visual, black screen. A deep, low hum builds in the darkness. Not music, but vibration. Subtle waves ripple across a void, and faint light, the echo of the Big Bang, flickers into view. Before there were stars, before galaxies, before light itself, the universe was filled with sound. Not the kind that passes through air or echoes in valleys, but pressure waves, ripples in a dense, hot plasma that filled all of space. It was a time when the cosmos was not yet transparent. A vast ocean of charged particles, electrons, protons, photons, all trapped together in a cosmic fog. And within that fog, the newborn universe sang. Its song was not silence, but structure, an ancient harmony of expansion, gravity, and heat. This is the story of the universe before light, a story written not in stars, but in sound. Imagine for a moment, the entire universe squeezed into a space smaller than a single atom. Then, in an instant, it erupts.
The Big Bang.
But what came next wasn't the silent, dark void we often picture. For the first 380,000 years, the universe was an impossibly hot, dense soup. It was so dense that light itself couldn't travel freely. Photons, the particles of light, were constantly bumping into charged electrons, trapped like a car in a traffic jam. This opaque, superheated fog is what we call the primordial plasma. Now, where does sound come into this? Sound, at its most basic level, is just a pressure wave moving through a medium. On Earth, it's air. In the early universe, the medium was this plasma. Two colossal forces were locked in a cosmic tug-of-war. On one side, you had gravity, pulling matter together, trying to make the dense regions even denser. On the other side, you had the immense pressure from all those hot, energetic photons, pushing everything apart. This cosmic battle of push and pull created vibrations, massive pressure waves that rippled through the plasma. These were the first sounds of the universe. These weren't sounds you could hear with your ears, of course. Frequencies were incredibly low, far below human hearing. Think of it as a cosmic hum, a fundamental bass note that vibrated through all of existence. These sound waves are called baryon acoustic oscillations, or BAOs for short. They were the universe's first song, a symphony of competing forces playing out on a scale we can barely comprehend. The peaks of these waves were regions of slightly higher density, and the troughs were regions of slightly lower density. So for 380,000 years, this cosmic concert continued. The universe was ringing like a bell. But then, a dramatic change happened. The universe had been expanding and cooling all this time, and it finally reached a critical temperature about 3,000 degrees Kelvin. At this point, it was cool enough for the free-floating electrons to combine with protons and form the first stable neutral hydrogen atoms. This event is called recombination. Suddenly, the photons were free. The cosmic traffic jam was over, and light could travel across the cosmos for the very first time. This first light is what we now detect as the cosmic microwave background, or the CMB. And here's the truly amazing part. When the universe became transparent, the music stopped. The pressure waves, the baryon acoustic oscillations, were frozen in place. The pattern of their peaks and troughs was imprinted directly onto the CMB. When we look at maps of the cosmic microwave background today, those tiny temperature fluctuations we see are the fossilized remnants of those primordial sound waves. We are literally seeing the echo of the universe's first song, a song that played for hundreds of thousands of years in the dark. These frozen sound waves didn't just disappear. Slightly denser regions they created became the gravitational seeds for everything that came later. Over millions and billions of years, gravity pulled more and more matter into these areas. They became the anchor points around which the very first stars ignited. And eventually, the vast cosmic web of galaxies we see today began to form. So, the grand structure of our universe, the placement of galaxies and galaxy clusters, is a direct consequence of a song that ended 13.8 billion years ago. The universe essentially sang itself into existence. It's a profound thought. Before there was sight, there was sound. And it was this ancient music that laid the blueprint for all of cosmic history. To understand the sound of creation, we have to travel back in time, way back, 13.8 billion years, to the very beginning of everything. At the instant of the Big Bang, our universe was a place of unimaginable extremes. Incredibly hot, fantastically dense, with temperatures soaring into the trillions of degrees. In this primordial state, matter and radiation were one and the same, a seething ocean of energy and particles colliding at nearly the speed of light. But this cosmic chaos wasn't perfectly smooth. Deep within it, it's tiny quantum fluctuations. Think of them as random jitters in the universe's density, created subtle variations. Some spots were slightly denser, others slightly less so. And these tiny imperfections were the universe's very first notes. Imagine it like this. Where matter was a bit denser, gravity tried to pull even more material in. But the intense radiation, countless photons bouncing off electrons, pushed back with immense pressure. This cosmic tug-of-war between gravity pulling in and radiation pushing out created a rhythm of compression and expansion, in other words, sound waves. These primordial vibrations, which scientists call baryon acoustic oscillations, traveled through the early universe like ripples spreading across a vast cosmic drum. Each wave was a dance between gravity and light, creating alternating zones of high and low density throughout the plasma. This was quite literally the first music of the cosmos, a deep, resonant hum that filled the entire observable universe. Now, you might think space is silent, but the early universe was different because it was so dense. Sound needs a medium to travel through, and for the first 380,000 years, that medium was everywhere. Every single cubic meter of space was filled with a glowing plasma of hydrogen, helium, electrons, and high-energy photons, all packed together so tightly that any disturbance would ripple outwards at about half the speed of light. This cosmic fluid vibrated like a living thing. Gravity would pull matter together, and the pressure from photons would resist, driving waves outward again and again. The specific size and frequency of these waves were determined by the universe's temperature, density, and what it was made of. It was a universe filled with resonance, a symphony of physical laws playing out on a cosmic scale. Of course, no one could actually hear it in the way we hear sound. The frequencies were far too low and the wavelengths were unimaginably vast. But the underlying physics is identical to how sound works here on Earth, at its peak. These cosmic sound waves carried energy on scales larger than entire galaxies. The whole cosmos vibrated with patterns that would one day decide where galaxies, clusters, and vast empty voids would form. But this cosmic concert couldn't last forever. As the universe expanded, it also cooled. Around 380,000 years after the Big Bang, the temperature dropped to about 3,000 degrees Kelvin. This was the magic number, cool enough for electrons and protons to finally combine and form neutral atoms. This moment is known as recombination, and it changed everything. Suddenly, photons, particles of light, were free. They could now travel across the universe without constantly bumping into electrons. The universe became transparent for the first time. But with this newfound freedom, for light came a profound silence. Once the atoms formed, the plasma that carried the sound waves was gone. The medium disappeared, and the music of the early universe faded away. But it didn't vanish without a trace. It left behind a perfect record. When those last photons broke free, they carried with them a snapshot of the universe's final acoustic moment, the exact pattern of sound waves, frozen in time and space. Today we can still detect those ancient photons. We call them the cosmic microwave background, or CMB, the oldest light in the universe. And embedded within the CMB's subtle variations in temperature is a fossilized echo of those primordial sound waves. Every tiny hot and cold spot you see in maps of the CMB corresponds to a crest or trough of an ancient cosmic sound wave. The cosmic soundscape, once dynamic and flowing, became a static image, a visual record of vibration, imprinted forever on the universe's first light. How loud was the universe back then? It's a strange question, but cosmologists have calculated an answer. At its peak, the sound waves would have registered around 110 decibels. That's roughly as loud as a rock concert or a jet engine. But remember, the sound was spread across unimaginable scales, with frequencies that took hundreds of thousands of years to complete one cycle. If we could somehow speed up time by an astronomical factor, the universe would have hummed with incredibly deep, resonant tones far below the range of human hearing, but rich with overtones that held the blueprint for all future structure. Think about that for a moment. The exact patterns of these ancient sound waves determined the large-scale structure of our universe. They decided where matter would gather to form galaxies, how large the great cosmic voids would be, and even how dark matter would cluster together. It is a stunning realization. The very same physics that governs how sound travels through the air also sculpted the grand architecture of the cosmos. In this cosmic orchestra, gravity played the part of the drum's skin, and the pressure of radiation was the hand that struck it. As the waves rippled outward, they tuned the scale of cosmic structure itself. So the sound of creation didn't just disappear, it simply changed its form. It was frozen into light, written across the fabric of space, and its echo is still visible today in the arrangement of galaxies and everything we can see. Before there was light, there was vibration. Before there were stars, there was rhythm. And before there was silence, there was the sound of the universe being born, the first and most ancient resonance of existence itself. Have you ever wondered what the universe sounded like at the very beginning? It might sound like a strange question, but the answer is written in the oldest light in the cosmos. When the universe was just 380,000 years old, it was a hot, dense soup of plasma. Then, it cooled enough to become transparent, releasing a flash of light that has been traveling across space ever since. We call this the cosmic microwave background, or CMB. At first glance, it looks like a uniform, faint glow across the entire sky. But hidden within this light are tiny, almost imperceptible variations in temperature, just 1 part in 100,000. These aren't random noise. They are the fossilized echoes of sound waves that once rippled through the primordial universe. They are the fingerprints of creation itself. The story of how we found this ancient light is a classic tale of scientific serendipity. Back in 1965, 2 engineers at Bell Labs, Arno Penzias and Robert Wilson, were trying to get rid of a persistent hiss in their new radio antenna. They tried everything. They rewired their equipment. They even cleaned out pigeon droppings from the horn. But the noise wouldn't go away. It came from every direction, day and night, with the same intensity. What they thought was an annoying bit of static turned out to be the greatest discovery in cosmology. That hiss was the afterglow of the Big Bang radiation from a time when the universe was a fraction of its current age, stretched and cooled by cosmic expansion to a mere 2.7 degrees above absolute zero. Every single microwave photon their antenna detected had been on a journey for over 13 billion years. What Penzias and Wilson heard as static was just the beginning. In the decades that followed, missions like COBE, WMAP, and most recently the Planck satellite, have turned that faint hiss into an incredibly detailed map. And what this map reveals is breathtaking. It's not chaos. It's a stunningly intricate pattern of hotter and cooler spots. These spots aren't just random splotches. They correspond to the crests and troughs of gigantic sound waves that were frozen in place the moment the universe became transparent. Imagine a vast cosmic ocean, ringing with sound. Then, in a single instant, that ocean freezes, preserving the shape of every wave. That's what we're looking at. The CMB is a snapshot of a universe that was literally singing. So what caused these primordial sound waves? It all started with the interplay between gravity and pressure in the early plasma. Tiny quantum fluctuations, born in the first fraction of a second after the Big Bang, created regions of slightly higher density. Gravity would pull matter into these dense spots, but as the plasma compressed, it heated up, creating an outward push of pressure, like a spring recoiling. This push and pull created massive vibration sound waves that propagated through the universe at over half the speed of light. These waves weren't just in the light. They were dragging matter along with them, creating shells of higher density as they expanded. When the universe cooled and the light was set free, these shells of matter were frozen in place. They became the seeds for all future cosmic structures. Amazingly, we can still see the imprint of these sound waves today, not just in the CMB, but in the way galaxies are arranged across the cosmos. When you map the locations of millions of galaxies, you find they aren't distributed randomly. There's a subtle repeating pattern. On average, galaxies are slightly more likely to be found about 500 million light-years away from each other. This preferred spacing is a direct echo of the size of those sound waves in the early universe. It's called baryon acoustic oscillations, and it's like finding the rhythm of the Big Bang written into the very fabric of space. The music of creation literally defines the architecture of our universe. For cosmologists, analyzing the CMB is like reading a musical score. By studying the size and strength of the different spots on the map, they can break it down into a power spectrum. This graph shows the intensity of the vibrations at different scales, just like a sound engineer might analyze the different frequencies in a piece of music. Each peak in this spectrum represents a harmonic, or a specific resonant frequency of the early universe. The first, largest peak is the fundamental tone, the biggest, loudest sound wave that could fit into the universe at that time. The smaller peaks that follow are the overtones, like the higher notes that give a musical instrument its unique character. And here's where it gets truly mind-blowing. By measuring the precise height and position of these peaks, scientists can deduce fundamental properties of our universe with incredible accuracy. The first peak tells us about the geometry of space itself, and it shows that our universe is almost perfectly flat. The second peak reveals the amount of normal, baryonic matter, the stuff that makes up stars, planets, and us. And the third peak helps us measure the amount of mysterious dark matter. The data from the Planck satellite has given us our most precise cosmic recipe yet. Our universe is made of about 5% normal matter, 27% dark matter, and 68% dark energy. All of that information, extracted from sound waves frozen into light over 13 billion years ago. The precision of these measurements is a testament to how far we've come. The final data released by the Planck satellite in 2018 provides a map so detailed that it perfectly matches the predictions of our cosmological models. It's a stunning confirmation that our understanding of the universe, from Einstein's general relativity to the strange rules of quantum mechanics, is on the right track. We can now simulate the early universe on a computer, modeling how those plasma sound waves would have behaved, and the result looks almost identical to the real map of the sky. It's as if we found a composer's original score and discovered it perfectly matched the symphony we were hearing. But what if we could do more than just see the score? What if we could actually hear it? In recent years, scientists have done just that. By taking the frequency data from the CMB power spectrum and translating it into audible sound waves, they've been able to play the sound of the Big Bang. They compress 13 billion years of cosmic history into just a few seconds. The result is not exactly a catchy tune. It's a deep, vibrating hum, which grows in complexity as higher and higher frequency harmonics are added. It's an eerie, profound sound. It's the sound of density waves sloshing back and forth through the cosmic plasma. For the first time, we could hear the echo of our own beginning. So why does all of this matter? Because without these primordial sound waves, we wouldn't be here. The slight density variations they created were the essential scaffolding upon which all structure in the universe was built. The slightly denser regions had more gravity, and over billions of years, they pulled in more and more matter, eventually forming the first stars, galaxies, and the vast cosmic web we see today. The slightly less dense regions became the great voids of empty space. The universe didn't just explode into being, it resonated into existence. Every ripple in that ancient plasma was a note in the song of creation, a melody that would one day give rise to planet's life. And eventually, a species capable of looking back and listening to its own cosmic origin story. Those faint patterns in the sky are so much more than just leftover radiation. They are the universe's memory. They are the frozen vibrations of a cosmos awakening. The sound never truly vanished. It just transformed, becoming the light we see and the structure we inhabit. The song of the universe is still playing all around us. Just needed to learn how to listen. The first symphony of the cosmos has long since faded. But physicists still ask, can we hear its echoes today? Is there a way to listen? Not to the light, but to the vibration of space-time itself? When the universe was young, sound traveled easily. Pressure waves rippled through the dense, hot plasma-like vibrations in water. But as the universe kept expanding, this plasma thinned out. At around 380,000 years after the Big Bang, atoms formed, light broke free, and the medium that once carried sound waves simply disappeared. Sound as we know it needs something to travel through. Atoms colliding, compressing, and rebounding. And once those atoms became neutral and scattered, the cosmos fell silent, at least in the way we usually think of sound. But silence in the human sense doesn't mean stillness in physics. Even in the empty void, the universe still vibrates in the very fabric of space-time itself. If the early universe's plasma carried acoustic waves, then space-time itself may have carried a completely different kind of sound: gravitational waves. Albert Einstein predicted them way back in 1916. He described them as ripples in space-time caused by massive objects accelerating. Every time two black holes collide, or two neutron stars spiral into each other, the fabric of the cosmos quivers. These events are so powerful they literally send waves through space and time. But what about the Big Bang itself? That first unimaginable explosion of energy, expansion, and creation must have generated its own gravitational symphony vibrations that should still be rippling through the universe today. These waves would be far older than the cosmic microwave background, the oldest light we can see. They wouldn't reach us through light, but through space itself. If we could detect them, we would be listening to the universe's original heartbeat. Cosmologists call this hypothetical signal the primordial gravitational wave background. It's a kind of cosmic hum that was imprinted on space-time in the very first trillionth of a second after the Big Bang. It isn't made of sound in air or even sound in plasma. It's geometry itself, vibrating. The theory goes that these waves were born during a brief but incredibly violent moment called cosmic inflation. In this instant, the universe expanded exponentially faster than the speed of light, stretching tiny quantum fluctuations to cosmic scales. Those fluctuations became the seeds of everything we see today: matter, light, and even the tiny temperature ripples in the cosmic microwave background. But alongside all of that, inflation should have also produced gravitational waves, a kind of deeper sound that even the CMB can record directly. So far, we haven't heard them. But for a thrilling moment, we thought we had seen their fingerprints. In 2014, the BICEPTA telescope, stationed at the desolate South Pole, made headlines around the world. Its team announced they had detected a subtle swirling pattern in the cosmic microwave background, a pattern called B-mode polarization. This twisting signal, they claimed, was the long-sought-after evidence of primordial gravitational waves. For a brief moment, scientists thought we had finally heard the universe's first breath. It was a monumental announcement. But just a few months later, the excitement dimmed. Further analysis from other teams showed the signal could be explained by something much closer to home: cosmic dust. Tiny charged particles floating within our own galaxy were twisting the ancient light, mimicking the signal they were looking for. The search hadn't failed, but the universe had reminded us that its faintest whispers are incredibly easy to mistake for noise. So, if we can't reliably hear these ancient vibrations through light, then perhaps we can detect them directly using gravitational wave observatories. Since 2015, LIGO, the Laser Interferometer Gravitational Wave Observatory, and its European counterpart, Virgo, have been successfully recording these space-time ripples from colliding black holes and neutron stars. Those detections opened a brand new era of astronomy, giving us the ability to hear the universe through its geometry. It's like we've grown a new sense to perceive the cosmos. But the gravitational waves from the early universe would be far weaker and have a much longer wavelength. It'd be too low in frequency for observatories like LIGO to detect. Instead of a sharp chirp, like a black hole collision, they would sound more like an ultra-low, persistent cosmic hum. Future missions like LISA, the Laser Interferometer Space Antenna, might finally be able to tune into these deep vibrations. LISA will be a trio of satellites flying in formation, forming a gigantic triangle in space, with sides millions of kilometers long. This massive scale is what's needed to catch the long, faint waves from the dawn of time. And if it succeeds, we will finally be listening to the original sound of creation, not just its afterglow and light. This all leads to a deeper mystery. What exactly is vibrating? If space-time can oscillate, what gives it this property, this elasticity? And if quantum fluctuations were the seeds for these waves, does that mean the vacuum itself, supposedly empty space, has its own kind of sound? Some advanced theories, like string theory, propose that everything in the universe is fundamentally made of vibration. They suggest that all particles and forces are just different notes played by tiny, resonating strings. If that's true, then the sound of the Big Bang might not just be a metaphor. It could be the fundamental mode of all existence. The first note in a symphony that includes everything. This is where physics starts to sound a lot like philosophy. Did the universe begin as a single, perfect note? The deeper we listen, the more patterns we find, and not just in physics. We see them in biology, in art, and even in consciousness. From the elegant spirals of galaxies to the steady rhythm of our own heartbeats, nature seems to follow harmonic principles. Could it be that the universe didn't just create sound, but that the universe is sound? A kind of standing wave evolving across time into greater and greater complexity. When we detect gravitational waves, we aren't just hearing distant, violent collisions. We're tuning into a universal resonance that began 13.8 billion years ago. A resonance that, through an incredible chain of events, ultimately produced us. Perhaps the universe has never truly been silent. Perhaps every atom, every star, and every thought is still part of that ancient song, the one that began before light. The echoes of creation are all around us, just waiting for instruments precise enough and for minds curious enough to finally listen. Have you ever wondered what the universe sounds like? We think of space as a silent, empty void. But what if I told you the universe has a voice? It's been singing a song for 13.8 billion years, and we've only just learned how to listen. In the moments after the Big Bang, the universe wasn't dark and quiet. It was a scorching, dense sea of plasma, ringing with pressure waves, like a bell struck at the dawn of time. Those ancient vibrations are long gone, but they left an echo, a memory frozen in light that we can still detect today. This is the cosmic microwave background, or CMB, and here's where it gets incredible. Scientists have discovered how to translate this ancient light into sound. Think about it. Every wave, whether it's light, sound, or even a ripple in space-time, has a frequency. The frequencies from the early universe are incredibly low, far below what our ears can hear. But they follow mathematical ratios, just like the notes in a musical chord. By taking the data from the CMB and dramatically speeding it up, compressing billions of years into seconds, we can shift these cosmic frequencies into the range of human hearing. This process is called sonification. It's not a metaphor. It's a direct translation of data into sound. And the result isn't random static. It's a haunting, structured hum. It has harmonics. It has a melody. When cosmologists first did this, they found a rising tone, a deep chord that slowly shifts upward as the universe expands and cools. The universe wasn't silent. It was singing. In 2003, NASA took data from its WMAP satellite, which measured tiny temperature variations in the CMB, and turned it into an audible file. The sound is a low, evolving drona cosmic bass note that gets higher in pitch over time. It's a literal audio recording of the universe growing up. Dr. Mark Whittle, one of the pioneers of this research, described the sound of the universe's first 700,000 years, condensed into just a few seconds, as the soundtrack of creation. But we didn't stop at the Big Bang's echo. Astronomers are now listening to the universe in all sorts of ways. Have you heard the chirp of two black holes colliding? That sound, recorded by gravitational wave observatories, is the sound of space-time itself being warped and twisted. Each chirp is the final violent cry of cosmic giants merging together. We've also translated the signals from pulsars superdense, spinning stars into rhythmic beats. They're like cosmic metronomes, ticking away with incredible precision across thousands of light years. And when we convert the data from gamma bursts, the most powerful explosions in the universe, they sound like sharp, percussive hits the universe's drum solos. These aren't artificial sounds. They are the voices of real cosmic events, carried across billions of years, speaking a language of frequency and rhythm. For the first time, we're not just seeing the cosmos, we're hearing it. What's fascinating is that this idea of a cosmic sound isn't new. For millennia, ancient cultures have spoken of a primordial sound, a sacred vibration from which everything emerged, the the logos, the music of the spheres. Philosophers and mystics intuited a connection between sound and creation. Now, science is confirming that intuition with data is what they imagined our instruments can now record. It turns out it was never silent at all. This isn't just for our listening pleasure either. Sonification is a powerful tool for scientific discovery. The human ear is incredibly good at picking out patterns, rhythms, and anomalies in complex data, things our eyes might miss on a chart. Astrophysicists now listen to data to find new patterns in the way galaxies are clustered. To detect the subtle dip in starlight as an exoplanet passes in front of its star, or to filter out noise from gravitational wave signals. Take Dr. Wanda Diaz-Merst, a brilliant astrophysicist who is blind. She relies entirely on sound to analyze data from space. By listening to the universe, she can hear phenomena that others might only see. Her work proves that our understanding of the cosmos isn't limited to sight. The universe speaks in a language that can be heard, felt, and understood through vibration. And those vibrations are all around us, and even inside us. Every gravitational wave from a distant black hole merger subtly stretches and compresses our entire planet. Radio signals from pulsars wash over us every second. We are quite literally resonating with the cosmos. Earth itself is like a giant instrument, and our telescopes and detectors are the microphones, tuned to the frequencies of creation. Ultimately, this connects us to the universe on a deeply personal level. When you hear that low hum from the Big Bang, you're not just listening to data. You're hearing the rhythm of the universe that gave birth to everything you know. Every atom in your body was once part of that primordial plasma, vibrating in that first cosmic chord. That sound isn't just out there, it's in our DNA. The universe has been playing its song for 13.8 billion years. And we are the latest note, the part of the song that has learned to listen back. We have taken ancient light, ancient motion, ancient silence, and turned them into sound. The song was never lost, just had to build the right ears to hear it. Every age of science begins with a new way of seeing. But this time, humanity found a way to listen. The universe's first sound was written in light, and our greatest instruments have spent decades learning how to read it. In 1989, NASA launched a modest satellite called COBA Cosmic Background Explorer. It was humanity's first attempt to map the faint microwave afterglow of the Big Bang with precision. A decade later, in 2001, NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, took the next step. Orbiting 1,000,000 miles from Earth, WMAP refined COBE's findings with far greater resolution, mapping the CMB across the entire sky in exquisite detail. It confirmed something extraordinary: the universe's age, composition, and shape could all be inferred from these ripples. WMAP's data led to what cosmologists now call the Standard Model of Cosmology. It's revealed that the universe is 13.8 billion years old, that it's flat, not curved, and that it contains about 5% normal matter, 27% dark matter, and 68% dark energy. With WMAP, the ancient sound waves of the cosmos became measurable, predictable, almost audible. The ripples of the Big Bang were no longer myth, they were mathematics. Then came Planck, launched by the European Space Agency in 2009. It was the most sensitive instrument ever built to study the cosmic microwave background. Planck's detectors were cooled to near absolute zero, reducing thermal noise to almost nothing. For 4 years, it mapped the sky with incredible precision, measuring temperature fluctuations down to 1/1,000,000th of a degree. The result: the most detailed portrait of the infant universe ever created. Where COBE gave us hints and WMAP gave us clarity, Planck revealed structure. Every single pixel of that map is a snapshot of sound, frozen ripples from when the cosmos was just 380,000 years old. What is the physics hidden in these ripples? By analyzing the power spectrum of the CMB, that is, the distribution of hot and cold spots at different angular scales, scientists could reconstruct the entire acoustic history of the early universe. The peaks in that spectrum correspond to standing waves in the primordial plasma, the universe's first harmonics. These measurements allowed scientists to determine the rate of cosmic expansion, known as the Hubble constant, the density of matter and radiation, and even the amount of neutrinos in the early universe. Planck didn't just look at the afterglow, decoded the score. It told us which notes the universe played, and in what rhythm. When researchers translated Planck's data into sound, they found that the universe's melody wasn't random noise. It followed harmonic patterns remarkably similar to those found in resonance systems right here on Earth. Each frequency represented a density oscillation. Each rise and fall, an echo of how gravity and pressure fought for balance in the early plasma. The resulting sound, a low, evolving tone that slowly changes pitch, is an audible bridge between theory and experience. You can literally hear physics in motion. The universe itself is the instrument. What makes Planck's discovery so powerful is their universality. The same acoustic patterns we see in the CMB appear in the large-scale structure of galaxies today in what are called baryon acoustic oscillations. These are literal imprints of those early sound waves preserved across billions of years of cosmic evolution. It means that the sound of the Big Bang is not just ancient history yet, still visible in how the universe looks today. Every galaxy, every cluster, every cosmic filament all follow the rhythm of those first oscillations. In a sense, the Planck mission didn't just map the past. It uncovered the geometry of sound itself. Planck's achievement was the result of unprecedented collaboration. Thousands of scientists, 50 institutions, and decades of development. Its instruments, the low-frequency instrument and the high-frequency instrument, worked together to cover a wide range of microwave frequencies, filtering out galactic noise and isolating the true cosmic signal. Every observation required absolute perfection, because the difference between success and failure was a temperature change smaller than 1/1,000,000th of a degree. When Planck's final results were published in 2018, they didn't just confirm our theories, they refined the constants of nature themselves. It was the sound of the cosmos, tuned to 12 decimal places. The combined work of Kobe, WMAP, and Planck transformed cosmology from speculation into a precision science. Before them, we guessed the age of the universe within billions of years. After them, we knew it within tens of millions. They gave us not just a map, but a timeline, the entire history of the universe, compressed into a pattern of waves and harmonics. It's as if the cosmos itself handed us its birth record, written not in ink, but in resonance. We have learned to listen to the universe, not through ears, but through equations. Every pixel in the Planck map is a note in the greatest composition ever written, the song of existence itself. We didn't just observe the cosmos, we decoded its rhythm. The echoes of the Big Bang have spoken. But they are not the only music written into the fabric of reality. If the early universe was a symphony of plasma and pressure, then the cosmos that followed still hums with new harmonies, just waiting to be heard. For most of history, our understanding of the universe was a silent movie. We watched the cosmos through light-visible, infrared, radio wave, breathtaking but muted spectacle. It wasn't until our own century that we finally began to listen. With the invention of gravitational wave detectors like LIGO, Virgo, and Kagra, we opened an entirely new sensory channel. We're no longer just looking at the universe. We're feeling its vibrations. Imagine a vast invisible grid stretching across all of existence. That's space-time. Now picture two black holes locked in a cosmic dance, spiraling closer and closer until they collide. This cataclysmic event doesn't just create a flash of light. It sends ripples, literal waves, through the fabric of space-time itself. Each time our detectors catch one of these events, whether from colliding black holes or merging neutron stars, it's not just a data point. It's a sound. When we translate these vibrations into something our ears can process, they produce a faint rising chirp. That chirp is the sound of cosmic titans clashing, a moment when the universe sings in the language of gravity, just like the acoustic waves from the dawn of time. These gravitational waves carry incredible information secrets about the structure, motion, and origin of the most extreme objects in the cosmos. They are the sound of the new universe played on an instrument we've only just learned to tune. But the universe doesn't just sing in high-pitched chirps. While LIGO hears the dramatic high-frequency cries of cosmic collisions, there's another sound, a much deeper and more ancient hum. There are gravitational waves so vast and slow that a single oscillation can take years to complete. Detecting these required a completely different kind of instrument. So, astronomers got creative. They turned our galaxy into a giant detector. They did this using pulsar timing arrays. Imagine a network of pulsars, incredibly dense, spinning neutron stars scattered across the Milky Way, linking with the precision of cosmic metronomes. By monitoring the timing of these pulses with exquisite accuracy, scientists can detect tiny shifts caused by gravitational waves passing through. In 2023, after years of patient listening, these arrays delivered a breakthrough. They found evidence of a gravitational wave background a deep bass-like hum that seems to fill all of space-time. What's making this sound? It's a leading theory is that it's the combined murmur of countless supermassive black holes merging at the centers of distant galaxies. It's the deep, resonant drone beneath the entire cosmic melody. It might even be the true continuation of that primordial sound of creation we heard in the cosmic microwave background, an echo that has never stopped reverberating. Speaking of the cosmic microwave background, it's only one snapshot and a single. Frozen echo from the moment the universe first became transparent to light. But what about the time before that? Before the first stars, before the first galaxies. There was an era known as the Cosmic Dark Ages. During this period, the universe was filled with a dense fog of neutral hydrogen. No starlight could escape. But even in that absolute darkness, the universe wasn't silent. The hydrogen atoms themselves were emitting faint radio signals at a very specific wavelength, 21 centimeters. If we could detect those ancient signals, we could create a map of the universe before the first lights turned on. We could hear how the very first structures began to take shape in the dark. This is one of the most exciting frontiers in modern astronomy. Projects like the Hydrogen Epoch of Reionization Array, or HERA, and the Colossal Square Kilometer Array, SKA, are in a race to capture this hidden symphony. These giant radio telescopes are straining to hear the faintest whispers from across cosmic history. If they succeed, they will allow us to replay the missing prelude, the earliest unwritten verse of creation's song. From the quantum realm to the cosmic scale, it's becoming clear that sound is more than just a metaphor. It's the tangible manifestation of vibration. Resonance and rhythm, the very principles that define existence. Atoms vibrate, stars pulsate. Galaxies collide in silent gravitational symphonies. Every oscillation, whether in air, in light, or in space-time itself, is a form of communication. A transfer of energy and information. This is why scientists are increasingly using a technique called sonification. By converting complex data from light, gravity, or particles into sound, we can tap into our brain's incredible ability to recognize patterns. Listening has become a new form of seeing. Helps us find the melody hidden in the noise, to feel the structure that our eyes might otherwise miss. And this deep connection to vibration isn't just out there in the cosmos. It's right here, inside us. We humans are creatures of resonance. The same fundamental physics that governed the universe's first oscillations also governs the vibrations in our atoms, the frequencies of our voices, and the steady rhythm of our own hearts. When we translate cosmic signals into sound, we're not just analyzing data in a way, we're remembering. We are a part of the universe that has become conscious of its own vibration. Think about it. It's a primordial hum of the cosmic microwave background, the sharp chirp of merging black holes. It's a faint, ghostly whisper of hydrogen from the cosmic dawn. Together, they form an ancient and ongoing song. And we, with our curiosity and our technology, have just written ourselves into one of its verses. And the orchestra is still expanding. The next generation of space observatories will take our cosmic listening to a whole new level. In the 2030s, the Laser Interferometer Space Antenna, or LISA, will launch. It will be a gravitational wave detector in space, a triangle of satellites millions of kilometers apart, capable of hearing the low-frequency rumbles of supermassive black holes merging across the entire observable universe. Other missions like LightByArt and CMBs are designed to look for faint, swirling patterns in the polarization of the cosmic microwave background. These patterns could be the signature of primordial gravitational waves, literal echoes from the moment of inflation itself, the very first fraction of a second of the Big Bang. And further, in the future, new quantum sensors might even be able to detect the subtle vibrations caused by dark matter, turning the invisible universe into audible information. Each new mission adds another instrument, another voice, to our ever-growing orchestra of discovery. The story of the universe is a story of vibration, from the first trembling plasma to the last fading pulse of dying stars. We began this journey looking up at a silent sky, but now we know. Silence was never the reality. The universe has always been singing. We just had to learn how to listen. And perhaps one day, when we finally understand its every frequency, from the highest chirp to the deepest drone, we'll realize that the song it sings is the very one that gave us life. Thank you so much for joining me on this cosmic soundscape. If you enjoyed this journey, ain't forget to hit that like button and subscribe for more explorations into the wonders of our universe. What cosmic sound do you find most fascinating? Let me know in the comments below. Till next time, keep listening.